Hi folks, in this short video I'm going to walk you through two of the problems that came up on a recent homework set. The first one was regressions involving stock market data, and the second was fitting models for age versus finishing time for a 10-mile road race that takes place every spring in Washington, D.C. So we'll go ahead and get started on the first stock returns problem. The corresponding R script for this that I'm working with here is saved as a HW2.R under the R scripts tab on the class website. So you can see, if you're sharp-eyed down here, that I've already loaded my market model dataset for this problem. I did so using the import dataset command, which is what you should do as well. And so away we go here. So part A asks us to simply make a summary table when we try to fit a regression for each of 6 blue chip stocks. So they're Apple, Google, Merck, Johnson & Johnson, Walmart, and Target. Those stock returns on a daily basis being the outcome variable in the regression, and the returns on the broader stock market we get the proxy variable for that, which is the returns on the S&P 500. Okay, so we fit 6 regressions, one for each of the stocks against the broader returns on the market, and I've just queued that up in 6 different lines here. I'll highlight this and hit Command Enter to fit all those models in one big fell swoop. And now we can start extracting information from those models to build our table. So for example, we can look at the coefficients, the alpha and the beta for the individual models. We can also look at the standard deviations of the residuals, which give us a sense of how much variability there is left in that stock after we've adjusted for its dependence on the broader market. And we've used this information to build our table. And what you're going to notice about this is that if you just go kind of bit by bit here, so let's try a different stock, for example, instead of Apple, we'll do Merck, or maybe Johnson & Johnson. What you're going to notice is that these betas are all positive. Most stocks are positively correlated with the market, so when the market moves up, the stock also tends to move up. And then the alphas here, the beta naughts, as we've been calling them, are mostly very small. So these are, the units here are percentage points, so we're talking about 0.04 percentage points, 0.07 percentage points. Which stands to reason. It's very difficult for a stock to, on average, outperform the market every single day, and by a big margin. And so this is giving you an estimate of to what extent the stock outperformed the market in any given year. And most of those alphas or beta naughts are pretty small. Okay, so that's pretty straightforward. We can use just these basic functions to extract model summaries to build our table. Let's look at Walmart more specifically. So here are the coefficients. It's an alpha of about 0.03 and a beta of about 0.47. And if we compare that beta to the one we get when we go to Yahoo Finance and look up just on the Walmart ticker page here what the beta that they're reporting is, the beta that I found when I looked here was 0.19, which is obviously quite a bit different than the beta that we calculated here, 0.47. And there's a number of reasons why that might be. So one explanation is simply sampling variability. Even if the underlying beta is constant over time, if Yahoo takes one sample and we take a different sample, then it stands to reason that we would get different answers. Now, could they be as far apart as 0.19 to 0.47? Maybe not. We'll learn to quantify the degree to which you should expect things to vary due to sampling variability. A couple of other explanations. First of all, we're probably calculating these betas on a different time span. We're using daily returns. You might imagine that Yahoo Finance would use weekly or maybe even monthly returns going back a little bit further than simply 1 year's worth of data. And another explanation here would be drift in the underlying market dynamics. So Walmart may respond to market shocks in a fundamentally different way in 1 year than in another year, and that reflects just change in the underlying dynamics of the market and the underlying dynamics of the stock itself. So we wouldn't necessarily expect these betas to be constant across a broad swoop of history here. So it's no surprise if you stop to think about those 3 possible explanations why we might have gotten a different answer than Yahoo does. But it does go to show that these quantities that mutual funds or financial websites report are not set in stone. They can change, and they are subject to error having to do with the way that you sampled the data and the way that you estimated the quantities that are being reported. Okay, so let's look now at the last question, which made a claim. So the claim was that Walmart and Target are the most strongly coupled stocks, even after we adjust for those 2 stocks' shared dependence on the broader market. So one way to attempt to answer this question would simply have been to look at the correlation between Walmart stocks and Target stocks. But that doesn't respond to the hypothesis that's advanced in the homework problem, because there's a caveat there. We want to evaluate the strength of that relationship once we adjust for the dependence of each of those stocks on the broader market. And so there's a key insight here, which is that that's a statement about the residuals from the regression models that we fit in Part A up here. If we look at this model right here, the model for Walmart, the residuals from that model represent the returns for the Walmart stock once we adjust for Walmart's dependence on the market. And similarly, the residuals from this model represent the returns for the Target stock once we've adjusted for Target's dependence on the broader market. And so it's the residuals from these regression models that are at issue here, and there was a bit of a translation that you had to make from an English statement to a statement about a statistical model, but that's the correct translation of that statement. And so let's start looking at some residuals. Let's plot the residuals for Walmart versus, for example, Target, and there looks to be a pretty clear, not necessarily strong, but pretty clear positive relationship there, versus Apple, Google, Merck, and Johnson & Johnson. And if you look at kind of those plots carefully, it's pretty clear that Apple and Google look uncorrelated with Walmart, the residuals from those models at least. And so let's focus on the other three, Target, Merck, and Johnson & Johnson, each of which showed some hint of a positive relationship here. And there's a lot of ways that you could quantify the strength of that association between the Walmart residuals and the residuals from one of the other models. Simplest way probably is just correlation. So if we compute the correlation between the Walmart and Target residuals, we get about 30% right here. Between Walmart and Merck, we get about 19%. And between Walmart and Johnson & Johnson, we get a still lower number, about 14%. So that's evidence for the claim that even once you adjust for their shared dependence in the broader market, there still is a substantial amount of correlation between Walmart and Target returns. And that stands to reason because they would respond to economic pressures in broadly similar ways, given that they're broadly similar companies. Okay, so that closes off our discussion of the stock market problem. Let's move on to the next problem, which is data from the 10-mile road race that happens under beautiful cherry blossoms every spring in Washington, D.C. So this data set is actually contained within the Mosaic data library. So we load the Mosaic data library, and then we load the 10-mile race data contained in that library using this command right here on my line 37. And now the 10-mile race is available for our inspection. So we could look, for example, at the first 6 lines of it. And we can see every line here corresponds to a runner. We've got their age and years, whether they're male or female. At races, they distinguish between the gun time and the chip time or the net time. So they shoot the gun to start the race, and then the clock starts. But it takes some runners a number of seconds or sometimes even minutes to actually cross the start line and have their little microchip start timing things. And so this is the relevant finishing time right here, not the gun time. Okay, so let's take a look. Let's look at net finishing time versus age. So it looks as if we plot the data here, and this is something we all have to look forward to as we get older, getting a little bit slower on average every single year. There's still a huge amount of dispersion. Plenty of older folks who are very fast, plenty of younger folks who are on the slower side, but still a broadly positive relationship here. As you get older, you get a higher finishing time on average. What is on average the time penalty associated for this sample for an additional year of age? Well, a simple way would be to fit a linear model here. So let's fit a model for net finishing time versus age, add the line, and then ask for a summary. And there's a lot of information on this summary output here, some of which we've learned to interpret and some of which we have yet to learn to interpret. But let's focus here on this slope right here. And that, incidentally, is the same slope you would get if you asked for a coefficient of LM1 right here, 8.18. So to interpret this, let's remember what that beta 1 means in a regression model. For a 1 unit change in age, that is for 1 additional year on your body's calendar, you, on average, would expect to finish 8.18 seconds slower. Okay? So that looks to be our population average estimate of the time penalty associated with 1 additional year of age. However, we could take a slightly different approach here, right? So let's fit two separate models here to two separate subsets of the data. One would be a model for men alone, and another would be a model for women alone. And the way we do that is quite straightforward. We just form subsets of the data based on the sex variable, M and F being the two levels of that variable here. And so I'll fit separate models, one for the subset corresponding to men, one for the subset corresponding to women. And there they are. And now let's look at a summary of these models. Give myself a little bit more breathing room here in the console. So if I ask for a summary of the men model, it looks like the coefficient on the age variable is a lot bigger than we had before, about 17.5 seconds. So the interpretation here, kind of going back to what we had from the previous model, one additional year of age corresponds to a 17.5 second slowdown on average for men. Okay, so let's try that for women. Let's look at a summary of the model that we just fit for the subset corresponding to women alone. And here it looks like the time penalty for an additional year of age for women is about 16 seconds, 15.96 here. So this is a little bit difficult to understand. If we compare it to the model we got by aggregating everybody and just treating everybody as part of the same sample here, we discover that on average for the whole population, the time penalty for 1 year was about 8 seconds. For men, however, the time penalty was about 17.5 seconds, whereas for women, it was about 15.9 seconds. So how could that be? How could the time penalty for men be 17 seconds, the time penalty for women be 16 seconds, and the time penalty for everybody be 8 seconds? Something's wrong with this picture. And so there's clearly a difference depending on whether we try to estimate this effect by aggregating everybody or whether we disaggregate and fit separate models for men and women. Let's take a look if we superimpose the plot of all three of those lines on this plot right here, just with slightly smaller points. Let's show you the line corresponding to the aggregate model with everybody, so a slight positive slope right there, line corresponding to the model for men, and the line corresponding to the model for women. And what's very striking about this plot is that the black line looks too shallow. The red line goes here, and the blue line goes here, and they're both noticeably steeper, even just on this plot right here. In fact, we'll zoom in a little bit so you can see this. The red and the blue line here are noticeably steeper than the black line. And so dealing with these paradoxes that can arise when you think about grouping variables in the context of regression modeling. Should we fit separate models? Should we fit one model? Should we require everybody to have the same slope and the same intercept, or allow different slopes and different intercepts? It's very easy to tie yourself in knots thinking these questions through, and that actually is the subject of a future chapter where we learn to systematically incorporate the effects of grouping variables in regression models. And one of the take-home lessons of that will be some tools that allow us to make the correct decision about whether we should go with the black line here as a population average or with the red and the blue lines here as separate models for men and women.